2 would be 8. Right? So it's just a numerical case or example of the general case. This is the general case. Now, what is J? This is actually not the absolute value, is a notation for determinant. So we call J as Jacobian. Okay, so you will learn this term in mathematical economics. Jacobian. So the Jacobian is a determinant, and this determinant would be non-zero. And this condition, which means the Jacobian, the determinant of the Jacobian, doesn't equal 0, is a condition to say something that now we have 6 variables, Q1, Q2, lambda, P1, P2, Y. And now, from the 6 variables, we may choose arbitrary 3 variables to be implicit function of the other 3 variables. So mathematically, we have Q1. We have 6 variables here, Q1, Q2, lambda, Y, P1, and P2. If you are a student from the Department of Mathematics, then the Jacobian would tell you that you may choose arbitrary, whichever 3 variables you may choose, like I choose Q2 lambda P1 to be function of Q1 Y P1 and another function Q1 Y P1 Q1 Y P1 sorry, not P1, P2. Once again, you may choose this, this, and this to be variables expressed by functions of the other 3 variables. You may do this, or you may change to like Q1, Q2, P1 to be functions of the other 3 variables. Whatever you want to do, you just choose 3 variables among these 6 to be implicit function, 隐函数 implicit function of the other 3 variables. But since you are a student of the Department of Economics, not mathematics, so we want to do something meaningful, do something with some meaningful intuition or explanation, interpretation. So we choose Q1, Q2, and lambda. From these 6 variables, we choose Q1, Q2, and lambda to be implicit functions of the other 3. The reason why we do this is because they are endogenous variables we may choose, we may decide. And these 3 variables are exogenous variables. External to the model, we cannot decide, we can just accept it. We can just accept them as exogenous. Okay? So we know how much money we have, we know the prices of the market prices of the goods. and we want to decide the quantity we consume, and also the multiplier. So in this way, is a perspective with economic sense. In this way, we may have economic sense. Okay? In this way, it's mathematically it's fine, but we cannot just interpret what are they. We just do not have any interpretation making sense. Okay? Once again, in terms of mathematics, you can do this, you can do that, you can choose whichever 3 variables among these 6 and make the other 3 variables as, you may choose whichever 3 as the implicit functions of the other 3 variables. But we don't do that because we wanted to have something make sense, making sense. Okay? What kind of sense? Economics. So the story is like this. We have an objective function. We wanted to maximize our utility. How can we do that? We choose the level or the quantities of x1 and x2 we are going to consume so that we can maximize our utility subject to the budget constraint. So whenever we have a combination of the prices, the market prices of good 1 and good 2 and our income, we may derive or compute the optimal values to consume. So this makes economic sense. But this just makes mathematical sense. Okay? So that's the difference. That's one difference between economics and mathematics. We economists use mathematics as a tool, helping us to analyze problems. But we are not dominated or dominant. We are not dominated by mathematics. Don't be a slave of mathematics, okay? Don't be a slave of mathematics. We are the master of mathematics. We utilize mathematics to help us analyzing problems. So we do something making sense. We don't do things like this. Although they are fine in terms of mathematics, but not fine in terms of economics. Okay, because we cannot say we cannot tell some story by this. Do you understand what I'm talking about? Once again, the theorem of implicit function, the implicit function theorem, allows us to do something like you may choose whichever you like, you want. Just pick 3 variables as the dependent variables. And the other 3 variables would be the independent variables. Okay? Mathematically, you can do anything. Just make sure that the Jacobian doesn't equal 0. So whenever you satisfy this premise, then you may do something by implicit function theorem. You can do things like this. But we economists don't do that because given this, we cannot tell a meaningful story. There's no meaningful story. Only this one, we can say something. Okay? We are choosing over the endogenous variable given the exogenous variables. Because for these variables, we can just take it. We cannot decide it. We cannot make it. We can make endogenous variables. Is that okay? Okay? All right. You don't, so this is something I just told you, a determinant or matrix is a 3x3 matrix, the determinant of a 3x3 matrix. And it's actually, there is another term, we call it Hessian. It's about the second order condition. So the second order condition for two variable problem looks like this. A little bit complicated, so I will not introduce in this course. But if you want to learn something more, just go to the mathematical economics class. All right. Let me show you something. It's actually a proof. This is actually a proof. Okay. Oops. Let's go back to the original problem we are facing. We want to maximize our utility subject to a budget constraint here, right? And we put down the Lagrange multiplier. Put down the Lagrangian function with the Lagrange multiplier here. And given this first order condition, we know the second term should be 0. So actually we are doing the same thing. We are maximizing utility. And now, since we have the optimal solution of Q1, the optimal solution of Q2, and the optimal solution of lambda, we may replace these three optimal values back into the original function. Just like if this is a function y equals f of x. Okay? And of course, if there is an x1, if there is an x2, you may have f of x1, you may have f of x2, right? So f is actually a function describing or specifying the relationship between x and y. Okay? Now, since we are maximizing the function value, and we already find x star, which is the critical value of x. Since we have the critical value, and we know the second order condition is satisfied, it's negative. So it's like an inverse U shape. And if we replace this value back to the function, we would have f of x star. Is that right? And we call this value as the stationary value. Do you remember that? The stationary value is the function value of the critical point, or the critical value. Okay? So we are doing the same thing. we just replace the critical values back to the function, and we would have lambda star equals q star, q1 star, q2 star, lambda star, q1 star, q2 star. Is that okay? So now, when we do this, we would have the stationary value of Lagrange. And the stationary value is the maximum. Okay? So now you know it is the maximum. And if we maximize, if we differentiate this function with respect to y, so now we call it, I give it a nu. So we do something, partial nu, partial y. Nu is actually the stationary value of Lagrange. So partial nu, partial y would have something u1. Y should like this. u1. And why there is a u1? U is a function of q1 star, q2 star. I don't see any y here, don't I? Do I see any y here? We don't see it, right? But don't forget, q1, q2 is actually a function of p1, p2, and y. So actually q1 star is a function of y. So although we don't see y directly here, but we know q1 is a function of y. So y affects q1 star, q1 star affects u. Is that clear? So by chain rule, u1 and partial q1 star, partial y. Okay? The reason why we can do this to this function with stars is because we already replaced the optimal value back to the original Lagrangian function, right? We've already replaced them into this, and we know q1, q2, lambda star are functions of p1, p2, and y. So we may differentiate q1 with respect to y. Y may affect q1 star, and q1 star may affect u because we have q1 star here. So we have u1 multiplied by this. This is the first term. And u2, because y does not only affect q1 star, but also affect q2 star, right? So partial q2 star, partial y will be the second term of the differentiation. And we have a multiple here, lambda star. Do you think lambda star is also a function of y? Yes, right? Lambda star is also a function of y. So partial lambda star, partial y, and with the square parenthesis, I just give it up. Plus lambda star, and differentiate this. Y, differential y with respect to y would be 1 minus p1 is something exogenous, cannot be affected by y. Alright? They are independent So partial Q1 star, this would be affected by y. Minus P2 partial Q2 star by y. Okay, done. Finish. And rearrange this. We may take Q1, partial Q1, partial y. We have another partial Q1, partial y here. So we take partial Q1, partial y out, and we will have a U1 minus, because there is a minus P1 lambda star, minus P1 lambda star, okay? And partial Q2, partial y, we have a U2 here, and we have another partial Q2, partial y here, so it's a negative P2 by lambda. And we have partial lambda, partial y here, and we have y minus P1, Q1 minus P2, Q2, and there remains a term, lambda star, okay? Now, here's the magic. This term in the parentheses will be 0. And this term will be 0. And this term will be 0. Why? These three terms in parentheses are all zeros. Why? Because we just use these three equations to solve the optimal value, right? To solve the critical points. So the critical points is actually a solution to these three first order conditions, right? So you put the solution back to the system of equation, the equation systems. You, of course, must satisfy the system, is that right? You derive your solution from here, and you replace the solution back to the equation system. Of course, these equations must be satisfied, right? Is that okay? So this would be the second one, the second first order condition, the third first order condition, and the first order condition, right? So they are 0, 0, 0. Okay, so something very clear. Lambda star remains. The total differentiation leave a single lambda star here. So let's interpret this. What does it mean? Y is our income. So partial nu partial y means if you give me $1 more, the marginal utility I may have, this would be the marginal utility we may have by $1 extra to our income. So one more unit of the resource can give us lambda star. That's why I just told you in the very first class today, I say, what is lambda? Lambda is the marginal utility of the resource, right? The marginal utility of the resource. Do you remember that? Now the resource is income. So you give me $1 more, I may have this marginal utility. So mathematically, I can show you that lambda has some economic interpretation. So lambda measures the effect of a change in y, okay, in income, in resource, on the optimal value of the objective function lambda. And we may also verify this, partial nu, partial P1. What does it mean? if the price of good one increases by $1, then our utility, the marginal utility, would be this, a negative sign with lambda and Q1 star. What does it mean? If the optimal solution for our expenditure on like pizza and burritos. So pizza and burritos. Do we have double R? I don't quite remember double R. Burritos. A single R or double R? Double R, right? Okay. Okay. Now we have pizza and burritos. We want to know if the price for pizza increases by 1. What does how we are going to be affected? So the price of pizza, P1, increases by $1. Do you think you will be happier or less happy? You will be better off or worse off? The price goes up, you will be better off or worse off? Worse off. Because the budget set would be look like this, right? So your budget set decreases so that you cannot choose on here. You can choose only on this new budget line, and your utility must decreases. Your utility must decrease, right? So we'll be worse off. And this term would be negative, which means worse. Lambda star Q1 star. So this is caused by this $1 thing. Okay? So it's the marginal utility for $1 more. But how much or how many units we are affected? It depends on the level of the quantity of pizza you consume. If you are a heavy lover of pizza, you eat pizza a lot per month, then this event, $1 more increased of the price will affect you a lot, right? But if you just don't like eat pizza, you eat 0 slice per month, you will not be affected at all. Do you understand what I'm talking about? So it depends on the quantity you consume. The effect of the change in the price of pizza depends on how many slices you consume. How many slices of pizza you consume, okay? So if you are a heavy lover of pizza, you eat pizza a lot per month, which means Q1 is large, right? So, for example, if you consume, say, 50 slices of pizza per month, so an increase, a $1 increase in $1 change in the price of pizza will make you you got to pay $50 more because you eat 50 slices per month. So for each month, you have to pay $50 more. but your budget constraint is constant. Your budget is constant. So if you spend $50 more on pizza, then what does it mean? You become $50 poorer because your income is cut by $50, right? So for each dollar you lose